Thank you so much. Can you hear me okay? Oh, good, right. Lovely to be here. I love doing public talks here in Oxford because it's always a really good audience. So, and you're going to do a little bit of work this evening. So I thank you all very much for turning up on a cold and, well, maybe just came here to keep warm, of course. I don't know. I wouldn't blame you. Okay, so that's my stuff, what I'm going to talk about. The title is connected to my new book, which is called The Art of Uncertainty, which is concerned with all those things. And the reason I'm sort of interested in this, when I was in Oxford, I got to Oxford when I was 18, God, about, more than half a century ago, and there, and I went to Keble College, and my tutor was Adrian Smith. I came to do maths, to do pure maths, and by halfway through the second year, it got too difficult. Banged my head on my ceiling of abstraction, and I turned to probability and statistics, which I stayed in ever since. And I was really grateful for that, to be able to do that. And so, but part of the important reason that I was sort of indoctrinated at an early age, because when Adrian Smith was my tutor, who's now president of the Royal Society, and he was translating a book by an Italian actuary called De Finetti about probability. And the point is that about De Finetti's idea of probability, the book starts with the statement, probability does not exist. We just made it up. And I've been mulling over this for 50 years, and I've decided he's right. So the book really is about how probability is an invention, it's a concoction that we humans, no wonder we're so bad at it, because we just made it up. It's not out there, possibly at a subatomic level, but even then I'm a bit dubious. So the whole point about the book is that it strongly suggests, or it just on the basis that probability is an expression of personal uncertainty. It's a personal expression of our ignorance, our degree of belief. And that ignorance might be about the future, or the present, or the past, but it's a relationship between us and the outside world. It's not a property of the outside world. All our probabilities will differ. So let me just demonstrate something that I'm going to do in the lecture anyway. So here's a coin, and what I'd like to ask is just, okay, before I toss it, what's the probability this is going to come up heads? Anyone like to suggest? 50-50. Yeah, you're quite happy about that, aren't you? No, you can't look at no, I know you're good. What a cynical group of people. Well, terrible, really. So I spun it, covered it up. What's the probability this is heads? Yeah, a bit grudging, a bit slow, but you got there. Now, what I've done is completely changed the meaning of that probability. The first bit of improbability was about what's called aleatory uncertainty, chance. Before I flip the coin, I cannot know what the result is. Now it's what's called epistemic uncertainty. It's my personal ignorance. And my ignorance is different from your ignorance. And that's going to come away. We're going to talk quite a lot about epistemic uncertainties. You putting your own personal ignorance into numbers. Actually, come on, have a look at the coin. Just look at both sides of it.
Yes.
It's a two-headed coin. Always good to carry one. And so the point about that is a beautiful £2 two-headed coin. I really treasure that. The point about that is, first of all, you shouldn't trust me. And secondly, that even your initial 50-50 was based on a judgment, an assumption. It was your personal answer. It was a judgment. It was wrong, but never mind. You did your best. And so my argument throughout this, and actually throughout the book, is that every probability we use in our daily life, in engineering, in climate change, and everything, is a construction. It's not a true number. It's a construction based on judgment and beliefs. So that's, anyway, I jumped through a lot of what I'm going to talk about, but there we go. Okay, so that's me. I used to do statistical methodology, clever stuff. Well, quite clever, not that clever, really. Bayesian stuff. Oh, yeah, look at that. We wrote that in the early 1990s. I was working on uncertainty in artificial intelligence in 1984. I mean, can you believe it? Nearly 40 years ago. We thought we had it solved. And look now, you put something into ChatGPT and it comes out with an absolute confident claim, and just writes a little print at the bottom, oh, it may be wrong. Sometimes I lie. I mean, really, that is not uncertainty communication in a trustworthy way. So we could talk about that later, but hopefully they're going to do a bit better than they're doing at the moment. But I used to do all this stuff, and then fortunately in 2007, I was philanthropically funded by David Harding of Winton Capital Management to do communication work. So I deliberately wanted to be a sort of Brian Cox of statistics. So I deliberately moved into making TV programs. There I am with Hannah Fry and another one like that. And there's me doing Wipeout, jumping over the big red balls in Argentina. I mean, honestly, you'd do anything for a bit of publicity. And I even got on Desert Island Discs during COVID. So, you know, I've sort of managed quite well doing all this stuff. And it's been great to have a second career, you know, run being an academic and all this ghastly publishing papers and all this nonsense, to turn into just be a performer. So I've been really, really fortunate and very grateful indeed. And I've written these books. Art Statistics has done very well. And that's the new book. Ba-ba! It's outside, selling at a discount, I know. So, and it's got all that sort of stuff in it. And I can't possibly talk about all those things, but they're all in the book. And basically it's me going blah about everything I can think of that I've been interested in for 50 years, since I got this indoctrination as a young student about probability. What is probability? Well, what is it? Nobody knows what it is. Nobody can agree. You can look up a definition and somebody might be confident about it, and they're wrong. You know, everyone, or certainly you'll find another confident definition just as quickly. So it's a whole area, is a bit of a mess, and I just want to hopefully sort out a little bit of it this afternoon. Yeah. So what is uncertainty? This is the definition I like: the conscious awareness of ignorance. And that, I said that ignorance might be about the future, the past, why things happened, what's going on at the moment. And that's the definition I use throughout the book, a conscious awareness, which puts it as a relationship between you and the outside world. And we've already done the coins thing, to say that, you know, about the different types of uncertainty, your relationship, how it's dependent on assumptions. And the crucial thing is about what I talk about this is deconstructing uncertainty. And we're going to do a bit of deconstruction this evening. And what I quite like this phrase is how to think slowly about not knowing. And not just say, oh, I don't know. No, come on, that's not good enough. We have to be a bit more analytic about it. So let me look at an example in history where there was a lot of uncertainty and how it was dealt with at the time. Bay of Pigs. It was 1961. Some of us can vaguely remember that. Looking in the audience, yeah, some can. Probably not that many, to be honest. The Cuban Revolution was in 1959 when Fidel Castro took over, and then by 1960 and 61, the CIA were planning to use 1,500 Cuban exiles supplied by the CIA to invade Cuba at the Bay of Pigs. I've actually been to the Bay of Pigs, beautiful place. But President Kennedy, when he was elected, when he took office in 1961, knew nothing about this. It was kept secret from everybody. The army didn't know anything about it. Kennedy found out about it, and he thought this was a pretty, you know, he wasn't really convinced at all, and he asked the intelligence report from the Joint Chiefs of Staff. And they were pretty gloomy about it. They thought, and I got a nice quote from this in the book, chances of success were about 30 to 70, about a 70% chance of failure. Unfortunately, by the time that report got to Kennedy, the 30% chance of success had been replaced by the phrase, a fair chance of success, by which they supposedly meant not too good. Well, I don't know how you interpret a fair chance, but to me that sounds pretty good. So not just because of those reasons, there's a lot of groupthink going on. Kennedy finally approved the invasion, and it was an utter fiasco. Complete and utter embarrassing failure. It encouraged the Cubans to invite the Russians in to put nuclear missiles there, and nearly led to a nuclear war the following year. We only just avoided the closest we've ever been to a nuclear war. So that was a total disaster, and a lot of it was because of the communication of uncertainty, taking the numbers out. So the point is that words might, could, perhaps, that we all use are really badly misunderstood by different people. And so what's interesting is that words like likely now have become standardized. They're standardized within climate change, they're standardized within different areas. So if you work for MI5 or MI6 and you say something is likely, you mean between 55% and 75% chance. You've got to mean that. Otherwise you don't use that. And the reason I know that is that I gave a talk at MI5 and they gave me a mug. Isn't that great? It's an official MI5 mug. And so what this shows is that when you've got only a little bit of coffee at the bottom, that's greater than 95%, meaning almost certain you need a refill. 55 to 75% means it's likely or probably you need a refill. Look, remember the Bay of Pigs assessment was 30%? Well, that would be officially communicated as unlikely to succeed in the British intelligence services now, which is a massive step forward. And other people have got these scales. There's a whole lot of scales used by NATO, broadly similar scales. So we've come a long way. Now, but these are subjective judgments. They're not real probabilities. These are purely subjective judgments. So I want to actually check about whether you can make a judgment about your ignorance. Okay, now, if you've got a pencil and paper, you might need that. You can do it on a calculator, or you can just do it in your head. You're clever people. You can do it in your head. So I'm going to ask you a series of questions. And they've each got two answers, A or B. And I hope you don't know the answer. No cheating, no conferring, and no looking at your phones. Don't want any cheating going on here. So there's A or B, and you've got to say which answer you think is most likely to be right, A or B. And then if you think it's A, then you've got to give your confidence. You say 10 out of 10 if you're absolutely sure it's A, and 5 out of 10 if you haven't got a clue. Then I'm going to tell you the answer, and then you're going to score your responses. And this is the scoring rule. This scoring rule is a work of utter genius. It was developed by weather forecaster Breyer in a similar format, not quite this format, but it's the Breyer scoring rule developed in 1951 to assess weather forecasters. It's a scoring rule used in all the super forecasting competitions by Tetlock and other people. For anything where you put a probability in an event, this is a really good scoring rule. So if you say, I'm 10 out of 10 sure, and you're right, you get 25 points. If you say 10 out of 10 sure and you're wrong, you lose 75. It's a really vicious asymmetric scoring rule. It's like a teacher who, if you do well, says, oh yeah, all right, but if you do badly, comes down on you like a ton of bricks. And so I'd like someone, first of all, to spot the formula behind that scoring rule, if you could, while you're doing this, and tell me later. Okay, first question, which is higher, the Eiffel Tower or Canary Wharf? So you've got to say which one you think is more likely to be true, A or B. This is pure epistemic uncertainty, A or B, and then say how confident you are in your answer. Okay, have you done that? Okay, and the answer is? A. So if you said 10 out of 10 Canary Wharf, you have got off to a really bad start. Okay, do you get the hang of it? You know what you're doing. Right, okay. Who's older, Prince of Wales or the Princess of Wales? William or Kate, who's older? No cheating, no conferring. Who's older, A or B? You're confident in your answer, and the answer is? Yeah, she's older than him. She's 6 months older than him. Okay, you get the hang of it. I hope you're not doing too badly already. If you're doing badly, one of the worst things you do is to try to be really more confident. Okay, which weighs more, a London double-decker bus, empty, or 2 average male African elephants? Two elephants, double-decker bus. Right. I would doubt anyone's too confident. Well, maybe you're confident. And the answer is? No, A. The bus is heavier than the 2 elephants. Which is larger, Belgium or Switzerland? Ignore the mountains. We're just talking about, cut around the horizontal area of it. All right, Belgium or Switzerland, which is larger? The answer is B. B is larger. And then finally, which is bigger, Venus or Earth? In terms of radius, okay. Which one do you think? What's the answer? B, Earth is bigger. Right, okay. So I'm not going to go through and ask you all your scores. What I'd like to ask, a different thing. Who got quite a lot of points? Who got more than, anyone get more than 50? Whoa, really good. More than 70? Wow, okay. So these people, they're either very lucky or they actually know something. Did some people do mainly just 5s and 6s, maybe an occasional 7? They're quite cautious and so stayed round about 0. Who is a cautious and a cautious assessor? Yeah, these are really good. These are reliable people because they know what they don't know. There is a third sort of person. And they might tend to get negative points. So who got negative points? Hooray! Now, a chimpanzee would do better than that, who just put 5 every single time. So you people who are worse than chimpanzees, is anyone willing to admit a spectacularly low score? Anyway, what did you get?
Minus 129.
Hooray! Can we beat that? Anyone get that? Okay. The people who get scores like that, do not have them as your financial advisors. You're not a financial advisor, right?
I'm a maths teacher.
Oh, maths teacher. Oh, that's fine. That's fine, yeah. Because people get very low scores, people who think they know things but don't. And these sorts of exercises are used as training for intelligence analysts so they stop being so overconfident, stop being so cocky. Tends to be a bit sex-linked, I find, about who gets very low negative scores, but never mind, I won't go into that. So this is a serious operation. What's the formula behind the scoring rule? Okay, if you want to subtract 25 from all the numbers, starting from the top right and working along and then along there. Subtract 25, and what do you get? You get 0, minus 1, minus 4, minus 9, minus 36. No, not minus 16, and minus 25. What's the pattern? It's the squares. This is squared error loss, that's all it is. You square the magnitude of your error. Instead of 10 out of 10, you square the difference. So it's squared error loss, slightly transformed, but it's still the same essentially thing. Now, squared error loss, you can prove that you need the squared, if you use squared error loss, it encourages honesty. If you just use a linear scoring rule that went, 25, 25, 15, 10, whatever, it would actually encourage people to exaggerate. If they were 7 out of 10 confident, they would say 10 out of 10, and that would increase their expected score. But this scoring rule is called a proper scoring rule. It encourages honesty. If you're 70% sure, you will say you're 70% sure. So what's this supposed to show is that you can assess probabilities that express your ignorance, your degree of belief, and your degree of ignorance, and you can use a scoring rule to assess those probabilities. There's no true probabilities. These are complete constructs. You just made them up. But you can use a score, and similarly you can use that scoring rule to assess any probabilities you give. So, okay, the other thing, I'm just in a little diversion, because this is a non-mathematical, we'll get back to some maths in a minute. Non-mathematical bits, I'm fascinated by luck. By that, I don't mean luck in the sense of people who think there's some external force that means I'm going to be lucky today, or something outside that affects it. What I mean is just a retrospective, looking at what happened and judge, whoa, that was lucky. Meaning, lucky meaning something that was unexpected, that was out of your control, and yet was good or bad. And I'm going to use family thing. That's my grandfather up there, Cecil Spiegelhalter, in the First World War. He had the bad luck to be born just at the right age to join the First World War as a soldier, which was pretty bad luck, I think. And then he had terrible luck of being in the wrong place at the wrong time. He ended up as brigade gas officer in the Ypres salient, just after the Battle of Passchendaele in 1918. And he had to do an exam, to qualify as a brigade gas officer, which must have been a job with a life expectancy of a couple of weeks, because he's had to spend the whole time walking around between trenches, exposed to shell fire, inspecting gas facilities. And he lasted 3 weeks in the job. That was what the landscape was like. He kept a diary, and he wrote narrow escape, lucky to get through in time, desolation. He was really lucky. So day after day, he was doing this job, getting shelled, and they missed him. And then they didn't. He lasted 3 weeks in the job. January the 19th, he went to Eagle Trench and Bear Trench, which we've actually visited, and he got shelled. Now, you can tell by the fact that the diary continues, and the fact that I'm here, the shell didn't land right on top of him. And he was blown up, and he was evacuated back, and he went declared B2, and missed then, was kept out of the front lines, and actually incredible bit of fortune is that because otherwise his battalion was then sent to the Somme, which in that time was a quiet sector, but in March 1918 met 1 million German troops coming over in the Kaiser offensive, and his battalion had to go over the top in a counterattack twice. And he was a second lieutenant subaltern, and he would have had to be first up the ladder, blowing his little whistle, encouraging his men, and I would not be here. I don't know who you would be listening to, but it wouldn't have been me. So, just there's a couple of things about that. The luck, what it reveals is different types of luck. Was he unlucky or lucky? Well, luck, I like this thing, it's the operations of chance taken personally. And it's something that's to do with being unpredictable, it's not in your control, and yet has an impact. And we experience this all the time in our lives, a huge amount of luck. And philosophers have identified types of luck. And I really love this. The most important type of luck is what they call constitutive luck, which is just who you were born as. Which is mad completely, you didn't ask to be born, you didn't choose your family. There you are, out you came by some chance event, which we won't go into at the moment because there are children in the audience. But anyway, by some bizarre event, which could so easily not have happened, there you are. And but this is a massively important. I mean, can you think of a child being born now into a nice family in the UK? There's many other places in the world they would not be a great place to be born, and there are lots of periods in history where it wasn't a great chance to be born. I reckon I had enormous constitutive luck in being born as part of the boomer generation. We ate all the pie. Everything went right for us. So I had an enormous constitutive luck. So Grandad had bad constitutive luck about when he was born. The next type of luck is circumstantial luck, which is being at the right place at the right time or the wrong place at the wrong time. And so he had very bad circumstantial luck, being in that place where the shell came over. And then it's outcome luck. He had fantastic outcome luck, which is just how it happened to work out for him at that period. And it's really interesting, I find, to deconstruct stories about this. So, there he is, lived till he was 81. So this plane crash, now I'm not old enough to remember this one, but it's quite a well-known plane crash that a DC-3 flew into Saddleworth Moor in 1949 in deep mist. And on board was my friend and statistician, Professor Stephen Evans. Many people might know him. I've worked with him in the Bristol baby inquiry, the infected blood inquiry. We worked together. Wonderful, wonderful man. And he was on that plane when it flew into the moor. So, Stephen's luck. He had terrible circumstantial luck of being on that plane at that time. He had fantastic outcome luck because he survived. Really unlikely. So where does the constitutive luck come in? The constitutive luck is because his father had been in the RAF and knew that the safest place in a plane was at the back and always made his family sit at the back. And it was only the people in the back row who survived. Everybody else was killed. So he was just born into the right family. Extraordinary, combination of the operation of chance taken personally. So I think it's very important. But of course, being, mathematicians, sometimes we want to start putting some numbers on things. Oh, hello, I've forgotten some of my props here. So the point of the constitutive luck, I mean, we always like to think that our successes are due to our hard work, and I'd love to think that whatever successes I've had were all due to my, all the efforts I'd made and that sort of thing. But in fact, we've got to admit that a huge amount of our success or whatever in life, or our difficulties we've had in life, are just due to who we were born as, our constitutive luck. It's hugely important. So what you're left with is this feeling of making the best of the hand you've been dealt, which is a popular phrase, but I think it's a really quite good phrase because it's a good analogy because we are all unique, biologically unique. We're all unique. Even identical twins will have very different health outcomes. They're not, they're not exactly the same. And why it's a good analogy is that every card shuffle is unique, essentially. So nobody in the entire history of humanity has ever shuffled the cards into that order before. Nobody in the entire history of humanity has ever shuffled the cards into that order before either. I'm confident that. I can't be logically certain, but I'm confident I would bet all the money in the world, as we used to say when we were small kids. And that seems really quite implausible. Why? And that's unique as well. Nobody's ever done that order before. So the only way of thinking about that, and the fact that it's not just nobody's done that one before, never in the entire history of humanity have two shuffles been done the same by anybody, ever. And I can be really, really confident about that. Why? Because you just have to count the number of shuffles. And the first card in the shuffle can be any one of 52, and the second one, any one of 51, etc., and we get 52 factorial. Now, I always say you should get out your calculators and start putting that number in, and very soon it'll fill up the screen, and after a little while, your phone will explode trying to do the sums, because it's a very big number. And you know, it's a big number, actually a bit bigger than that, and actually it's a bit bigger than that. And oh, I forgot some zeros. That's how big it is. It's about as many as there are atoms in our galaxy, the number of shuffles. And in the book, I do some sums and show that if everybody in the entire history of humanity had done nothing in their lives except shuffle cards, the chance that anybody at any time would have had the same shuffle is 10 to the minus 19, roughly. You know, so that's essentially as close to zero as any practical thing could be. So it is extraordinary, and this is a situation quite often, and we're going to do some examples in a minute, where probabilities are, we're surprised that things are as likely as they are. But this is one where we're surprised that things are unlikely as they are. And what it goes to show again is our intuition about probability is terrible. And people say, oh, why do people find probability so difficult and unintuitive? It's because it's difficult and unintuitive. I finally worked out after 50 years working on it, it is difficult and unintuitive. And it's not intuitive because we made it up anyway. So that's my thing. So that's so coincidences, I quite like coincidences. You know, why do they happen? They don't happen to me, because almost all coincidences are about people, not all, but a lot of them are about people noticing things. Oh, I sat next to somebody and they'd gone to the same school. I went on holiday and my friend was there. I did all that stuff. Now, I never notice anything. I never talk to anybody when I'm traveling. I wouldn't notice if my children were in the same room, because I'm wandering around like that all the time. So they never happen to me because I'm so unobservant. But I did get 6 double-yolked eggs. What about that? And 1 in 1,000 eggs are actually double-yolked. So when this has happened, before there's been a newspaper article that said that, oh, well, that must be a 1 in a million chance that that's happening. Well, no, I don't think. If it was that small, it would never happen. It would only happen about every 500 million years. So, but I got 6 double-yolked eggs. So I will tell you how I did it later on. Sometimes we can do the maths for coincidences. So this is a fairly common story. People who've got 3 kids in their family, under 18, and they've all got the same birthday. So this family, they're all born on January the 29th. Robin, Ruby, and Rebecca and little Ruby, who was a mistake apparently. So I hope she doesn't mind, that's what the father said. Anyway, but they're all got the same birthday, January, saves on birthday parties. So what's the chance of that happening? You could say, well, Robin set the date, because there's nothing special about January the 29th, except it's the day my grandfather was blown up, if you remember, which is a coincidence. And so the probability that Rebecca was born on that day, assuming uniform distribution over the dates, is 1 over 365. The probability that Ruby was born on that day, assuming uniform distribution, which is quite a big assumption, is 1 over 365. You multiply those up, you get about 1 in 135,000, it's about 7 in a million chance of that happening. But always with these, and that sounds, wow, amazing, tiny chance. What we should always do is say, yeah, it's amazing for them. Is it so amazing to hear about that? Is it so amazing to read this article? So what you have to do is to say, look at, well, how many families with 3 children are there? There's about 1 million families in the UK with 3 kids under 18. So that means there's about, at any one time, there's about 8 of them who've got 3 kids all with the same birthday. Just to Poisson distribution. So we don't know who they are necessarily, but just by chance, that's what had happened. And then when you start Googling this, there they are, they pop up all over the place. Except this was the Daily Mail, who said the chances were 48 million to 1. So what do? They put in another 1 over 365, which of course is irrelevant. If it really was 48 million to 1, it wouldn't keep happening. One after the other, it wouldn't keep happening, you know. So it's not 48 million to 1. It's much more common than that. So it's rare, but it's not that common. My favourite example for this, which was September the 19th, was the publication day for my book. And that was just a coincidence, because it's actually Hunt Rod's Day. Hunt Rod's Day is an amazing day. The Hunt Rods of Whitby is the most extraordinary family. They were both born, Mr. and Mrs. Hunt Rods, born on September the 19th, 1600. They were both married on September the 19th, 1620. They had 12 children, and they both died on September the 19th, 1680. On their joint 80th birthday, they both died on that day. I desperately want to know what happened. I don't know, was the cake poisoned? Did the floor collapse at the party? What happened on that day? And if you go to Whitby, there's all the Dracula stuff, but go up to the church, up near the Abbey, the parish church, and you'll find this memorial to the Hunt Rods, who I think should be hugely celebrated in Whitby. But this is a nice example. This is the Joyce and Ron Pulsford, a couple. They were both 80 on the 8th of the 8th, 08. I was asked to calculate what's the chance of that happening. I think I did some sums, but anyway, it's pretty unlikely for that to happen. It's a wonderful example of that, of just chance. Yeah. So birthday coincidences, though, happen a lot. We know that if you've got 23 people in a room, there's a 51% chance that 2 of them have got the same birthday. Well, more if they've got twins, but we don't count that. Forget that. It's 50, so 35 people, there's an 81% chance that 2 share a birthday. 80 people, so it's absolutely certain that 2 people in this room share a birthday, for example. You only have to get to 80, and there's 99.99 chance. So because randomness is clumpy, just because 80 people, it's not that the birthdays are then nicely separated by 3 days each. 2 will share a birthday. Okay, bit of maths. Ready for some maths? It's a very useful a very useful bit of maths. So you can do these sorts of calculations quite quickly, because I'm going to pretend there's 200 people in the audience, which are roughly, and I'm going to be able to do some sums in a minute because you're going to be working. Now, the very useful rule is if there are many opportunities for an event to occur, a rare event to occur, and the expected number, the number you expect to happen on average is m, then the chance that there's no events is e to the minus m, roughly. Closely, very close, remarkably close. E to the minus m. So I won't try to explain what e is if you don't know, but it's on the calculator. It's 2.718. A very really important number in mathematics, and it's e to the minus m. So quick proof, for those who don't want to follow this, just ignore it, doesn't matter. But if these were independent rare events, n each with a probability p of occurring, and so you expect m equals np. The chance that none occurs is 1 minus p to the power n, 1 minus p times 1 minus p times 1 minus p. So you can rewrite that as np over n, which is 1 minus m over n, which those who've looked at, have studied E, will recognize is about e to the minus m. So it's a simple one-line proof of why you just need e to the minus 1. I'm going to look at, in a moment, what we're going to do are dependent events. They're not independent, but that's all right as well, because if you assume the number of events is approximately Poisson with mean m, the probability of 0 events then is e to the minus m from a Poisson distribution. And if you don't know any of that stuff, it doesn't matter at all. It just means I've got a formula for checking things on you. So it means that 23 people I can essentially do on my head, or at least with a calculator. Because there are 23 people comparing birthdays. So there's 23 times 22 divided by 2 is 253 pairs. Each pair is a probability 1 over 365 of a match. So the expected number of matches is 253 divided by 365 is about 0.7, 0.69. And if you look at your calculators, e to the minus 0.69 is 0.5. So there's about 50% chance of a match. So you can do that, and you can do these sums for any number really quickly on a calculator. Okay, so in the Women's World Cup, people usually talk about the 23 because there's 23 people on a football pitch. The 2 teams of 11 and the referee. So half of all football matches have got 2 people with the same birthday. But they also, World Cup, the squad has got 23 members, which is nice. So if you look at the Women's World Cup, they had 32 squads, each with 23 members. You would expect about half the squads to have somebody with the same birthday, and 17 dead on, well, not quite dead on, but, Poisson, had at least 1 pair with a matching birthday. Brazil, Colombia, and Denmark had 2 pairs of shared birthdays. Morocco and Nigeria had 3 pairs. And Nigeria is lovely. There's 2 who are born on Christmas Day. And one's called Christy and one's called Glory, which is lovely. Lovely pair, both born on Christmas Day. So half of the World Cup squads have got 2 people with the same birthday in them. Okay, so a useful rule. Okay, well, let's try that. Now I'm going to try this with you. Because I could just do, if you've got 20 people, then there's an 87% chance that if they look at the last 2 digits of their phone number, there'll be a match. Now, I could pick 20 people and go along there, but what I'm going to do is ask you to turn to your neighbour on each side and say your birthday, not the year, the birthday, and the last 2 digits of your phone number. And just make a note if you either get a match or one away with one of your neighbours. Okay, can you just talk to both of your neighbours on each side? Oh, sorry, you haven't got it. Oh, you can talk. Okay. Have you done both sides? Okay. Have you done both sides? All right, okay. Well, okay, let's say there's 200 people here. So I thought there'd only be 100 people here tonight. So I'm really pleased. Let's say there's 200 people. That means there's 400 pairs of neighbours. So there's 400, it's like if you all shook hands, there'd be 400 comparisons that have been made. Let's look at the last 2 digits of their phone number. There's a 1 in 100 chance of a match. So there should be 4 pairs of people, roughly, who've got the same last 2 digits of their phone number. There's Poissons, so there'll be a lot of variability. Are there any pairs with the same last 2 digits? One up there, 2. So 1 there, and 2 there, and 2 there. Were you going to sit next to each other? No. So I got 3 pairs of people with the same, oh no, 4. What about that? Thank you. God, that's pretty good, I think. I said there'd be 4 pairs of people who the last, I didn't know who they were going to be, dead on. Oh, that was lucky. Yeah, and I was almost certain there was going to be that, because e to the minus 4 is almost 0, and so the probability that there wouldn't be any matches was very short indeed. So I thought that's not bad. Okay, let's look at, so I can work out the probability of at least much match, but it was e to the minus 4, must be 99 point something %. Birthdays. Okay, now 400, a 1 in 365 chance of a match. I'd only expect 1 pair to have the same birthday, one pair, and the chance that therefore there's at least 1 match is 63%. So there's about a 2/3 chance there's 2 people sitting in the audience with the same birthday sitting next to each other. Is there anybody in the audience with the same? Did you know? You knew. You're not twins. No. But you knew. Oh, you got the same birthday? 2 pairs. Yay! Thank you. Okay, so I expect 1, but Poisson 2, that's just fine. I'm not going to complain. I expected to get 1 on average, but I got 2, so that's just variability. So that worked quite well. Thank you very much. That's great. Okay, I didn't even have to cheat with Fed. So that's how you can do the sums. I did it. I would put 400 there, etc. And we don't even have adjacent. Who got adjacent birthdays and was 1 day away? People next to each other. There should be a lot more of those. Yeah, okay. I went 2 pairs. Oh, I thought there should be more because the 400 e to the minus 2. So I'd expected 2 pairs. No, I expect 2 pairs to 1 day away. So and that's what I got. Honestly, chance is working really nicely for me today. A couple of days ago I did one with some school kids, and I had something going, and I knew there was an 81% chance of it working, and it didn't work. Oh well, bad luck. So randomness is clumpy. But we know how clumpy it is. We can test it. Now this is a nice game. This is the game of trays, which is, I just want to test your mathematical intuition. So the game is, they used to play it around 1700. Somebody had all the clubs, and somebody else had all the diamonds, and they shuffled them up, and they played snap. So they just turned over cards one at a time, and if they had the same, both turned over the 4, or both turned over a 6, then they said snap, or something, trays, or something like that, and whoever said there were going to be a match, won. Do you think, which would you rather bet on? That there's going to be a match? Who would rather bet on there's going to be a match? Who thinks that's more than 50-50? Like, there will be a match out of 13 cards. Who thinks it's more likely there won't be a match and would bet on that? Well, some people aren't giving an opinion. I don't blame you. Okay. Well, let's do the sums. There's 13 cards. The chance that any particular pair will match is 1 over 13. But there's 13 opportunities for that to happen. Now, they're not independent, but it doesn't matter because expectation is a linear operator, and it doesn't matter if the events are dependent. So that's 13 times 1 over 13. So the expected number of matches is 1. So the chance that there's no matches is e to the 1 over e, which is 0.37. And the chance that there's at least one match is 0.63. So the people who said they think there's going to be a match will win nearly 2/3 of the time. But note one thing. It didn't depend on how many cards there were. 13 doesn't come into the calculation because it's 13 times 1 over 13. If each person had a whole pack of cards, 52, and turned them over one at a time, there's still a 63% chance they get a match. As long as there's more than 5. You know, with 1 or 2 cards, it's not close enough. But once you get 5, it doesn't matter how many there are in there. It's called the hat check problem, and it dates back to the original author where people checked their hats in at the. God shows how old this stuff is. They checked their hats in at the opera house, and then all of the tickets just got handed back, fell down, and got handed back around them. What's the chance that somebody will get, at least one person will get their own hat? It's 63%, regardless of how many people were handed their hats in. Now, I don't know about your intuition. My intuition is not good on this. Really, that it doesn't depend on the number of cards. So if you had 1,000 cards each, there still would be a 63% chance that you'd get at least one match. Okay, so Euler worked out the exact formula. Euler's work on trace is really, really nice. Works out the sum of the series, which converges very rapidly to 1 over e. Okay, have you recognize this guy? Okay, Darren Brown. So he's an illusionist. You may have seen this program. It was on nearly 20 years ago, I think. So I'm just going to show that. I hope this works. What he's going to do.
Side and tails on the other. But I want you to watch this and try and work out how it can be possible, because the key to understanding this is the key to understanding the system.
He's going to flip a coin, and it come up heads.
10 heads in a row.
10 heads in a row.
Watch.
It's not like my coin.
1. That's heads.
That's what he says he's going to do.
2. That's heads. 3. Heads. Heads, that is 4. Heads, 5.
They're not cutting the film. It's a single take.
6. 4 more to go, and I'll stop. 7. 3 more. 8. 9 heads. Last one. 10. 10 heads in a row. Thank you very much indeed.
Okay. How did he do it?
He spent a very long time filming it.
No, it's not flicking.
Sorry?
It's not flicking.
Oh, he was. No, it's proper spin, I think. I think it was a proper spin. I don't think the flips were manipulated.
There was a long series of ones where he didn't get 10, which he didn't.
Oh, you're so cynical. Are you suggesting we didn't see all the film?
That's exactly what I'm suggesting.
Okay, the cynical person here thinks that we didn't see all the film. We only saw the bit where he flipped it and got 10 in a row. So, was he unlucky or unlucky? Okay, so was he lucky or unlucky? So I'm going to show, this is how he did it.
10 heads in a row. Watch.
Oh, yeah.
To predict a run of 10 heads in a row and then make it happen is hugely unlikely. The chance of it happening is about 1 in 1,000.
2 to the 10.
However, if you flip a coin thousands of times and record the results, somewhere along that line of heads and tails, a line of 10 heads is actually very likely to appear. Okay, 10 heads in a row. That's 1. To work out the system, you need to understand that we can only know what comes from our own limited experience. And our experience can often be very far from the truth.
So how long do you think he took?
I can't see the ball anymore. Here we go. 10. What you saw was the final minute of what was an excruciatingly long day. We filmed for over 9 hours until eventually a clear
9
run of heads
hours
appeared.
of filming.
9 heads. Last one. The impossible became inevitable.
So do you think
10.
He
10
was
heads
l-
in a row. Thank you very much indeed.
So do you think he was lucky or unlucky to take 9 hours? Do you think that was a long time, or do you think he should likely to have done it before that?
Was persistent.
Yeah, amazing. And he looked like the first, he's very professional. Each time he had to look like it was the first time. So very professional. But do you think 9 hours was a long time or a short time to do it? What's your intuition on that? Yeah, I think it's good. Who thinks that was a long time? He was unlucky to take that long. Yeah. Who thinks he was lucky and he could have taken even longer? Yeah, but a mixture of opinions, difficult. Okay, we can do the sums. The probability that he'd succeed, is, as you said, is 1 over 1,000 roughly, that he'd do it at any particular attempt. An attempt is something that ends with a tail. But and on average then, you'd expect to take 1,000 attempts. But there's huge variation around that average. I reckon he took about, he didn't say this, about 1,600 attempts, because I've filmed how long it took him to flip it, and how many attempts in 9 hours, how many attempts you'd expect there to be. And I reckon he took about 1,600 attempts. I think he was unlucky to take that long, because on average he should have done it in about 1,000. And my colleague James Grime repeated the feat. He did it in an hour. And it's on YouTube. It's the most boring video you could ever think. He's flipping away. But again, he's got a cut where he only uses the last minute. So he did it. James Grime repeated the feat, and it took him an hour. Now, how can we do the sums about this? We use what's known as the geometric distribution, which is the waiting time before the first time something happens. So the probability of success in any particular attempt is p, 1 over 1,024. So the probability that the very first time he gets it the first time is 1 over 1,000, is p. That's probably gets it first flip 10 times in a row. I mean, you wouldn't have believed it. The probability that he does it at the second attempt is 1 minus p times p, because he failed the first time with probability 1 minus p, and then he did it with probability p. And the probability that the first success is at the nth attempt is 1 minus p to the n minus 1 times p. And that is the geometric distribution, and that's what it looks like. The most likely time is the very first flip. That's the most likely time to get 10 flips in a row, is the very first flip. Because to take longer than that, you've had to have failed earlier. So the probability of taking exactly 1,500 is, much lower than the chance of doing it at the beginning. But James was up there and Darren Brown was down here. So he was really unlucky to take that long. I don't recommend trying it. It really is immensely tedious to find out where you are on that distribution. But it is just an application of the geometric distribution. So finally, where did I get my double yolked eggs from? I bought a box of double yolked eggs. I know. It's a bit like the double-headed coin. It's a cheat. And I checked, that was a little while ago, and I just checked recently on the web, last week I looked, and you can get them from Waitrose, you can get them from Tesco's, cheaper in Tesco's. And I don't know what's so special about these. Anyway, so I do recommend now a trick. Buy a box of these, and then sneak into a friend's house and switch the eggs over. And they'll say, they keep on cracking them, oh my God, it's another double yolk. It's a great Christmas trick. I'm going to try it. Yeah. So, and I think that's it. Good luck. Thank you very much.